Okay, we're going to take a look at finding the maximum area here. So this is an optimization question. So it says, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and what are its dimensions? So the key word here is largest area. So this is how we know it's an optimization. We're looking for to optimize area, and it's area of a right triangle. So we could write that formula, half base times height. And you know, our plan is that we're going to, if we're optimizing, we're going to take the derivative of that and set it equal to 0. Okay, so we need to now look for what is reining this problem in and stopping that area from being infinity. So we're looking for the constraint, and we see that we have a hypotenuse of 5 centimeters. So the constraint, okay, is that, I'll just draw a picture of it because that's easy to do, that the hypotenuse is 5 centimeters. So we have a base and a height here, and we somehow want to make sure that we incorporate the constraint into the area formula so that that 5 centimeters is taken into account inside the area formula. And then once we have that, then we can find the derivative and set it equal to 0. So we're just going to set up this relationship. So h squared plus b squared will equal 25. And now I can just replace one of the variables. It doesn't really matter which. So I can choose h squared equals 25 minus b squared. And then I get that h equals the square root of 25 minus b squared. And, you know, normally I'd say plus or minus, but because we're talking about length, we'll just look at the plus. So now what I'm going to do is replace this h with this in this formula. That also gives us, you know, an equation with two variables, the b and the a, so that's also good. So we have a equals a half b times 25 minus b squared, and then I'll just put that to the 1/2 so that it's easy to take the derivative of that. Okay, so now I'm going to find the derivative, and I'm going to use the product rule here, with this being my first and this being my second. So we will get first derivative of the second times the derivative of the inside, so just the chain rule there, and then plus second, and then the derivative of the first, which is 1/2. Sorry, I'm running out of room here. Just going to move this over. Okay, so again, I did first derivative of the second, second derivative of the first. Let's move that 1/2. Okay, and then I'm going to set the derivative equal to 0 and solve for b. Okay, which isn't great here, but let's see what we get. Okay, so these cancel, and I get minus b squared over 2, and then I'll just put this square root on the bottom here. And then I have plus the square root, and then over 1/2. So we could just multiply both sides by the denominators here to get rid of them, or get a common denominator and put these together. Either way. So if I just multiply everything through by 2, 25 minus b squared, that should work. And so I still get 0 equals minus b squared, and then plus 25 minus b squared. When I multiply through by that, the 2's cancel, the square roots cancel. And so then I get minus b squared and minus b squared. So I can move 2b squared to the other side. And then I get b squared equals 25 over 2. And then I get b equals plus or minus, but again, the minus doesn't make any sense in the context of the question. So I get that the base is 5 root 2. And then I can go back up and solve for h. So h squared is going to be 25 minus b squared, which is 25 over 2. It's just easier to solve it as h squared than as h. And then we'll just square root it at the end. So I can get a common denominator here, 50 minus 25 over 2. And so h squared also gives me 25 over 2. And so h is also 5 over root 2. Okay, so an isosceles triangle is going to give me the biggest area. And the area would be a half the base times the height, which gives me 25 over 2 times 2, 4. And this would be centimeters squared. So that's the area, and these are the dimensions. And that's the maximum area. So when the triangle is isosceles, we get the largest area.